If you're looking for a content explaining how to easily create cluster within Proxmox, then this episode is for you. Welcome back to the Is It Observable YouTube channel. Today's episode is going to be part of the Kubernetes series, and you will see it's going to be a bit different from usual. For several months, I have faced limitation using cloud provider like AWS or Google Cloud for specific use cases. In fact, I need to have complete control on the configuration within my Kubernetes clusters, which led me to start building my own lab. I initially considered sharing my journey building this Homelab, but there wasn't anything interesting to learn. In fact, to be frank, there are already amazing content creators already out there covering this topic pretty well, so no value to add extra content here. However, today I'm super excited because I finally find the perfect angle to discuss about my Homelab by covering an impressive project that allow me, to launch a cluster with a single command line, and I'm referring to the Cluster API. The foundation of my Homelab is based on Proxmox. Why? Because many colleagues often recommended it. It was a natural choice as I needed an open source or a community edition of a virtualization solution. And there aren't many other viable options. If you do enjoy today's content, don't forget to like and subscribe to the channel. So let's see what we're gonna cover during this episode. I will start with a quick tour of my Proxmox setup and on the hardware I'm using. Then I will explain what is the Cluster API. I will explain how to build a cluster on Proxmox using the Cluster API. And last, how to observe the Cluster API. My Homelab journey at its core is around Proxmox virtual environment, which means Proxmox VE. If you never heard about it, but I doubt, it's the equivalent of vSphere from VMware. What makes Proxmox amazing is the ability to easily manage both virtual machine powered by KVM, containers utilizing LXC, so Linux containers, all accessible through a very easy, user-friendly web interface, and more than just a web interface, it also have an API, meaning that automation is also possible. The beauty of Proxmox also lies in its simple installation and setup process. It's designed to be accessible even for those who have never been administrating any servers. To configure Proxmox, it's a straightforward process. Step 1, first, you need to obtain the Proxmox VE ISO installer, so you can go directly to the websites. Then step 2, you need to create a bootable USB disk. Step 3, simple boots the machine that you want using the USB disks, and follow the very simple wizard-driven installation process. Once installed, access to the web-based management UI through the browser, and all it takes for you to start provisioning virtual machines or even containers. Then, if you have more than just one server, then you can also consider to create a cluster and join the new server freshly installed to the main cluster of Proxmox. On the size of the hardware, it would rely pretty much on what you're planning to achieve with Proxmox. For those who's eager to embark on their Proxmox journey, here is a list of resources that could be useful within your journey. So first you have the Proxmox installation guide, the Proxmox documentation, in fact, and then a couple of tutorials that you could use to start building your Proxmox. As my own lab expanded, I quickly realized that relying on a local storage across individual mini PC was insufficient, especially with a growing number of VMs and Kubernetes clusters. This led me to integrate a dedicated NAS into my setup. For those building their own lab, there are two primary approaches to build NAS implementation. So first, utilize a commercial NAS appliance, like there are a lot of vendors like Synology or QNAP, or build a custom NAS that involves using a dedicated machines and install a specialized NAS software such as TrueNAS or FreeNAS. There are plenty of tutorials, in fact, if you look around on YouTube, on how to create a NAS using a lot of different hardware, and also, if you want, on a Raspberry Pi. But keep in mind on something. important. A custom NAS would completely bring value for my Homelab, but if I was dealing with a media or video post-production NAS, then the hardware requirements would be completely different because you need speed on the network side, you need speed on the read and write access, you need a significant cache, so it's a completely different story. I've decided to choose the second options and have decided to install TrueNAS on a mini PC. TrueNAS is an open source or community versions of a NAS operating systems developed by IXC System, and they are providing, of course, enterprise support. The advantage of TrueNAS is the simple UI, allowing you to configure the NAS in a very simple way. It starts with all the right protocols required for a NAS, and it's very simple to configure snapshots. The installation process of TrueNAS is similar to Proxmox. First, get the TrueNAS ISO, put it on a bootable USB disks, boot your machine from the USB, and follow the setup wizard. Simply. Then configure your storage pool and datasets using a UI. And last, set up a user account and share folder accessible over the network. So here are a few links related to TrueNAS. So what is TrueNAS? How to use TrueNAS, the official docs, and a couple of step-by-step guides building a TrueNAS NAS with TrueNAS. In my current setup, the NAS will serve as a central repository for VM disks, ISO, and backup used by Proxmox, which simplify the resource management and also cluster scaling. You'll see that. The NAS will be an important point when using the cluster API with Proxmox cluster having several nodes. On the hardware side of my Homelab, I had to adjust the machines over time, driven by a constant desire of having more environments. The initial design principles were clear: very short costs, power efficiency, and ensure everything was racked mount. I don't want to have pile server racked every here in this desk. The journey began with a pair of surprisingly capable budget mini PCs, demonstrating that you can do massive stuff without a big investment. So I used, in my case, a BMax B6 Pro, which has an Intel Core i5 with 4 cores, 16 gigs of RAMs, and 512 gigabytes of SSD. And the second machine was a BMax B4, similar size, but here we have an Intel N100 processor. To create the first rack, I decided to go with the T0 server rack from PyHunt. It's small, it's cute, it makes sense for 2 nodes. It was perfect at that time. The initial rack also needed to have the essential network components, so the router for internet connectivity, the Ethernet switch, the various devices that will manage the local network for my Homelab. However, as my ambition grew, I had to move into more demanding workload, like running multiple virtual machines, and it became clear that more processing, more memory was needed for that. So I had to invest in more machines. So I decided to go for an Hypo-G mini PC. So it's a Ryzen 5700 processor. So that has 8 core. It's perfect for virtualizations, 32 gigs of RAM, and a 512 SSD hard drive. And then I had a GMTech M7 that has a bit the similar specs than the other ones. So at the end, 4 nodes, great, but the T0 rack, you can clearly imagine it does not work anymore. So I had to upgrade to a larger rack, the T1 from GitHub. This provides the right space for all the Proxmox nodes, so the 4 nodes, and the original T0 rack. Then, rather than being retired, I found a new purpose as a dedicated enclosure for the NAS. So now that I have my cluster, I initially started to manually provision VMs and configure the operating systems, install the components required for Kubernetes, and I did this process for 1 master node and 3 worker nodes. And then suddenly one crashed, I had to recreate everything, and I quickly realized that I wanted to have a simplified process on creating cluster, to have a similar experience than using a cloud provider, like a CLI, where I could just quickly spin up cluster without going through the manual configuration. And one day, I discovered this project that will bring all my requirements into reality, and the project name is the Cluster API. The Cluster API or CAPI will be the perfect solution for you if you're looking to automate the cluster creation within any type of infrastructure. The Cluster API is a sub-project from Kubernetes designed to manage the entire lifecycle of Kubernetes cluster using the traditional as code approach that we're using when using traditional Kubernetes. This means that instead of engaging into a manual process for provisioning nodes, installing Kubernetes components, and probably meaning building complex scripts to orchestrate everything, the Cluster API will allow you to define your cluster with a set of YAML files. What do you need to utilize the Cluster API? Well, we need a few things. We need a Kubernetes cluster that will host the Cluster API. Then you need an infrastructure. So on the infrastructure side, that is done because I have my Proxmox cluster. So let's see the installation. To install the Cluster API within this cluster, the easiest way would be to use their command line called clusterctl. The Cluster API has also an operator, but I'm not sure if all the providers are currently supported. If you're using the Cluster API operator with Proxmox, please drop a comment. I will be very interested in your experience. When using the Cluster API in an empty cluster, we would initialize by using the init command that will be in charge of installing the core components of the Cluster API. In fact, when initializing or even creating cluster, we will rely on a provider. A provider is in fact a hardware provider, so it could be a traditional cloud provider like AWS, GCP, Azure, or many others, or it could be a local one like VMware, or in my case, Proxmox. It could be also Kubernetes. Also, it has a support for vCluster, where it will basically be creating namespaces within our new clusters, for our new cluster. As you can understand, the Cluster API will reach out to the provider to provision the infrastructure layer, then deploy the actual cluster, meaning the control plane of our future cluster. And in fact, for the cluster control plane, there are also several types of providers, such as kubeadm, Talos, K3s, micro Kubernetes, and many more. So here is the full list of all the providers, infrastructure, and control plane providers. But how are the Kubernetes clusters created? Well, they are key components that the Cluster API would rely on. So first, we need an infrastructure, and for this, we'll require a provider to be installed and configured. By configuring, it means how the Cluster API can interact with the provider, so the actual requirement will depend on the provider that you are planning to use. In the Cluster API, you will have a dedicated namespace with the workload responsible to spin up the infrastructure. It is usually deployed as a deployment. It has a service exposed that will be used by the control plane of the Cluster API to delegate the creation of the infrastructure. Once the machine is actually provisioned, then it would be a component named Bootstrap that would be responsible of generating the right certificates, deploying the future control plane in the new machines. Bootstrap is also responsible of joining the new machines to the workload cluster. In our Kubernetes Cluster API, we would also have a dedicated namespace from the Bootstrap pods responsible for those actions, and similar to the infrastructure provider, there will be a service that the Cluster API will use when building clusters. Then we have the actual control plane. The type of control plane, of course, depends on the provider that we've decided to choose. The control plane will trigger the creation of the control plane by relying on the Bootstrap. Control plane holds the entire settings and collects the status of the various components. The control plane will also have a dedicated namespace, and the workload depends, of course, on the type of control plane that we have configured in the cluster creation. Last part is the networking part. There is also a dedicated namespace that will get the IP addresses of the machines, report them, and let the control plane be created. Finally, the main boss triggering the entire flow is the Cluster API. So it has the Cluster API system namespace. It is technically the operator that will trigger the cluster creation based on specific CRD. The Cluster API relies on sets of CRD to generate clusters. So at the end, this operator continuously observe and react to the CRD that has been deployed, representing our desired cluster configurations or updates. Meaning that all our cluster configuration would be YAML files. So it would be easy to store them in our version control, GitHub, Git, whatever, and rely on Argo CD, cross-planes to deploy our cluster or even scale our cluster. So there are various CRDs. We have the cluster. This is the top level resource serving as the Kubernetes cluster. It will get everything related to the general cluster properties, such as the network configurations, the reference to the infrastructure, and also the control plane provider as well. Machines. Each machine represents an individual node within our target cluster. This can be a control plane node or a worker node. But the machines are immutable. It's designed to be created or deleted. It's a bit like the pod concepts in Kubernetes. So that's why if you have a pod, meaning we have a machine deployments. To create or update the machines, we rely on the machine deployments that are used to manage the groups of worker nodes or control plane. They define how worker nodes are scaled, updates, replace the number of replica, ensuring that the desired nodes counts is there, and doing some rolling updates in case we want to change the worker nodes pools. The infrastructure resources, they are basically specific to the infrastructure provider that we've defined. So this infrastructure piece will define how the virtual machines or nodes are provisioned on the choosing infrastructure. For example, in my case, in Proxmox, we have the Proxmox machine templates that would specify which VM templates to use, the network interface, the type of disks, and more. Then we have the control plane CRDs. The cluster creation will need a control plane to be defined. So depending on the provider, so here in my case, kubeadm, we have the kubeadm control plane that will hold the kubeadm configuration that would be used. The cluster API has more CRD that are designed to keep track on the status of the cluster, the health, or even keep track on the creations. So configuring all those CRDs could sound a bit complex when you start. And the good news is that the cluster API CLI will simplify a lot the cluster creation. So clusterctl has a command called generates that would be in charge of generating all the various YAML files to create the cluster of our choice. Then we can simply apply to generate the actual cluster and ask the cluster API to start building the cluster. As usual, to prepare this episode, I have created a dedicated GitHub Repository with all the steps required to get started with Proxmox on the cluster API. So let's start with the actual requirements on our Proxmox cluster. So you will need to create a Proxmox user using the specific authentications Proxmox VE authentication server. This user would be needed to have specific roles, so the PVE admin role, because he will be in charge of creating the VMs, the templates, copy the templates over various nodes. A lot of different actions. So putting that role will be required. Once the user is created, we will need to create a token linked to that user. This token will be, of course, used by the cluster API to interact with our Proxmox instance with the Proxmox API. Before creating the cluster, the most important thing is to build a template that the cluster API could rely on our Proxmox cluster. For this, there is a dedicated project from the cluster API named the image builder that will help us to build the right ISO and create the VM template that we would need to use for our future cluster creation. So here is the link to the image builder project in GitHub. To build the template, you will have to define a set of environment variables defining where to store the ISO, in which node of your Proxmox cluster, the type of disks, the type of CPU, and the default size of memory and default size of CPU. To build this template, we will need to first run the command collecting all the various dependencies, then select the type of operating systems that we would like to build for our templates. To build the ISO and the VM template, we will need to run the command build Proxmox, and of course we precise the type of operating systems. This will in fact be in charge of downloading the operating systems, upload the ISO in Proxmox, then create the VM with the settings that we have defined, and last convert that VM as a template. Once we have our VM template, make sure to keep the ID of the VM template because it will be required when we will create our future cluster. If you're using a NAS, then make sure to store the VM hard drive in the NAS folder and not locally. And if you don't have a NAS for now and you plan to have it later, don't worry, you can start local and then change your template by migrating your disks in the Proxmox UI into the NAS once you have the NAS, of course. Now that we have a template, we can start utilizing clusterctl command line. So if you don't have any available cluster, I would recommend to start using kind to create a local cluster. Once that cluster has been started and your kubeconfig has been updated, you can use the clusterctl init command. Once the cluster API cluster is created with clusterctl, we can now create our first cluster in Proxmox. Again, for this, we need to define a certain number of variables, defining the future IP address of our control plane, the IP range for the nodes that will be spin up by the cluster API, the IP address of your local gateway, and more. Then, like explained, we will use clusterctl generate that will build the YAML files that we need. This will generate all the CRD based on the generate actions. Note that generate command will define the Kubernetes versions and the actual size of your cluster. You can still modify it later on YAML file. To create the cluster, we will simply need to apply the YAML file against the kind cluster. So kubectl apply -f and the YAML file. Then to get the status of our cluster creation, we can use clusterctl describe and the name of the cluster. That will show us where we are in the cluster creation. So we'll start have the machine ready, and then it will deploy the actual control plane like I explained before. And in fact, if you have not defined any CNI, the cluster won't be ready until you have deployed the CNI. So to achieve this, you will need to get the kubeconfig of our new cluster that is currently generated in Proxmox, and then use kubectl --kubeconfig options to point to our new cluster and apply the CNI of our choice. In this tutorial, I decided to use Calico, but you can use whatever you want. Then you can check the status of your cluster until all the nodes are actually ready, so the control plane, of course, and the worker node. Once this cluster has been actually created, we want to use this new Proxmox cluster to host cluster API for future cluster creations. So to achieve this, very easy, we will first need to initialize the cluster API again in the Proxmox new cluster using clusterctl, but here pointing with our kubeconfig that we have coming from this cluster. Once the cluster API has been deployed in the cluster, we can now move the content of our kind cluster into the Proxmox cluster. And this is great because the CLI has an action called move. So here, clusterctl move, and then we can say to kubeconfig. So basically, it will migrate everything to that the cluster that we have in Proxmox. Once the cluster API has been moved, we can finally delete our kind cluster and merge our kubeconfig to use it for future cluster creations in our Proxmox cluster. Currently, the observability of cluster API is a bit limited, but future improvements are actually planned within the project. So it's going to be probably going to add tracing, that's great, improve the logging and improve the metrics. The cluster API does produce metrics as of now. They are currently designed for maintainers to report the cache or a couple of resource usage. Until we have those metrics and tracing implemented, we are pretty much limited to gather information about the cluster API through the following methods. So first, the resource usage. So for monitoring the consumptions of the various pods of the cluster API or all the namespace, we can use tools like kubestate metrics or the node exporter, or even property solution like Dynatrace operator. Then from the logs perspective, they are all producing logs, so we can collect those logs produced for all the various workload of the cluster API, and the logs will allow it to identify the build process, identify potential errors. So logs can be easily collected using the OpenTree collector or Fluentbit. If you use the OpenTree collector, you will use the file log receiver, no surprise, and also the Kubernetes attribute processor to enrich that logs that you have collected. Then you have the CRD monitoring. So cluster API utilize many CRD as discussed. So we can collect the cluster API CRDs to track on the number of cluster, the current status, all other relevant details. So to extract this information from the cluster API CRDs, the OpenTree collector has a receiver called the Kubernetes object receiver that could be configured to pull the content of defined CRDs from the cluster. This requires, of course, to give the right privileges to the collector with the right cluster role on the desired CRD. And given the large number of CRD, it doesn't make sense to collect all of them. So we would focus on the most important ones. So the cluster that will help us to get details about the status of the control plane, the infrastructure, and the cluster size. Then we have the infrastructure provider, in my case, Proxmox, to obtain details to specific related to Proxmox itself. Then we have the actual control plane. So here in my case, kubeadm control plane, to identify any issues during the node provisioning. Especially this means focusing on specific CRDs. So cluster machine deployment for the cluster, Proxmox cluster, Proxmox machines from the infrastructure, and also we can technically add machine deployments as well to get infrastructure on the cluster API level. Then on the control plane level, I would say kubeadm control plane. That will give you most of the detail. To enable the collector to access to those CRDs, the service account used by the collector needs to be granted with the following API groups. So here is the list of all the various API groups and verbs and so on that you need to add in your airbag. Regarding the metrics, even if the cluster API currently expose a very limited number of metrics, if you plan to scrape them, the collector services account also need to be adjusted. All the metrics endpoints require SSLs. So to enable scraping those metrics, you need to add this piece to authorize to access to the /metrics endpoint. Then to be able to scrape all the various parts that expose metrics, you need to create a service on each cluster API components. So here is all the services I've created. And last, we need to create the right scrape config in our OpenTelemetry collector. While currently the metrics obtained are not super detailed, I'm still focusing on a few things. I'm focusing on reconcile errors to keep track on the errors that could happen when we reconcile our clusters, the number of active worker, so with control runtime active workers, and each cluster creation generates a workflow, and we can keep track on its duration using worker queue durations per second. Then if there is any task that is being queued during the creation process, we can look at the worker queue depth and also monitor any retry task using worker queue retries total. Based on these details, I have built a very basic dashboards that rely on the logs, on the Kubernetes objects that has been pulled out as a log, on few metrics, and of course on the resource usage. That's it for today's episode related to the cluster API. I have joined two topics, building a Proxmox cluster and sharing my experience with my Homelab with using Proxmox. So, and then of course explaining all the journey I went through with the with cluster API itself. I think the Clusters API project is an amazing project for automating the cluster creation, and specifically if you use, like I do, Homelab clusters, it will make your journey so much easier. I think on the observability side, like I discussed, it could be improved, but I looked at the GitHub repo and there are currently discussions on improving this. So cross the fingers, this will happen soon, and we'll probably have some tracing about the cluster creation and everything. So I think that would be super exciting. Aside of that, if you're more interested in details about Proxmox, also Proxmox monitoring, because I started to collect the metrics and I've started to build also a collector receiver to simplify the observability journey, in fact, for Proxmox. Let me know, because it's currently ongoing work that I'm doing here. So if you're interested to have details about it, let me know, and I will be very happy to share those details, and of course let you utilize those components if you're using Proxmox like I do in your Homelabs. If you enjoyed today's content, don't forget to like and subscribe to the channel. So see you soon for another episode.